Hey friends, it's good to be back with you. And today it's time to start complex numbers. Now, if you're like a lot of people, when you hear about complex numbers, you may get a case of the willies. I guess I should pause here. If you didn't grow up in the United States, you may not have heard about the willies, but you know what they are. This is when you hear about something and it makes you go, okay? That's the willies. Well, if you're thinking about complex numbers, there's no need to get the willies. Complex numbers are really pretty basic once you get past a couple of initial ideas, and they're not that hard to work with. Now I'm going to show you the mechanics of how to work with them, but before we do that, let's make sure we understand where they came from and why they seem so alien. All right? So let's start with a simple polynomial, the simplest one there is. So if I draw, the usual axes here, that's x, and that's y, and I draw this, okay, that function right there is y equals x squared plus 1. Okay, so where are the roots? Well, it doesn't cross the x-axis. Well, didn't they tell you in, I don't know, junior high school probably, that when a function crosses the x-axis, there's the root? Let's try this. Well, what would the root of that look like? Well, let's see, x squared plus 1 equals 0. If you solve that, you get the root, you get x. Well, looks like x squared equals minus 1, so x has to equal plus or minus the square root of minus 1. Well, we know now, we call that I for imaginary. Unless you're an electrical engineer, I was being used for current before double E's figured out that you needed complex numbers for essentially everything they do. And so if you're an electrical engineer, the square root of minus 1 is j. All right, so if you see that, don't be too surprised. Don't let that freak you out. Don't let it give you the willies. We know this now. Well, really most of human existence, this was not accepted. Algebra as we know it right now really only kind of coalesced into a coherent thing in probably the late Renaissance. Before then, people routinely came across things like this and just threw it away as being aberrant or somehow not a legitimate mathematical entity. Well, some brave souls kept it and started, worked through it, and they kept finding out an unsettling thing is if you retain this term, this one that didn't seem to make any sense, you kept getting the right answer. Well, you can only do that for about so long before you have to accept that there must be something here. And there is. There's a very, very well-established foundation of proof under all of this. If you can go to any math department and they'll let you take a class on complex analysis, which is based around this. So here's this thing called a complex number. Well, why was this so upsetting? Well, math for essentially all of human existence was counting. That's what it was for. How old are human beings? I don't know, 100,000 years maybe. Let's say it's about that. Well, math as anything but counting has only existed for the last couple thousand years. So 99.5% or something like that of human existence, math has only been counting. It's very recent that it's been anything but that. So you don't need this to count. You don't have 3 plus 2i sheep or 1 minus 6i children. It just never crops up in everyday life. It only crops up when you start using mathematics to describe the world around you, and the world around you can get pretty complicated, complex. So this is what's going on here. One of the first things we need to get out of the way is the names, okay? Any complex number, a complex number is just one that has a real and imaginary term. Oftentimes it gets called z, I guess just for tradition. If I call that a plus ib, that's the general form. Well, let's say this is 1 plus I. Well, this is a complex number. It has a real part and an imaginary part. The real part is 1, and the imaginary part is 1i, or just I. Now, when I become king of the world, we are going to change this. It is not going to be known as real and imaginary. It's the worst name ever. I don't know, up, down, left, right, red, blue, something like that. Anything but real and imaginary. Because when you call this imaginary, it makes it sound like it's not a legitimate mathematical entity. It absolutely is. It's always been there. It just took us until surprisingly recently to find it. Right? It's always been there. So if you want to think about this in the bigger picture, I guess, there are two kinds of numbers. There are real numbers and there are imaginary numbers. They are independent of one another. You cannot express one in terms of another one. I cannot express I in terms of real numbers. I is this. Okay? I cannot express a real number in terms of imaginary ones. There's no way to break this down into some more fundamental relationship. Yeah, I can Mickey Mouse some expression that includes only I that'll actually have one as its solution. But these are independent of one another. We generally plot them perpendicular to one another on axes. They're orthogonal to one another. So these are the two kinds of numbers. They're unrelated to one another. Okay, that's it. There's no way to break this down into any more simple form. You just can't do it. So, if you're thinking through this, you might wonder the thing I wondered. Well, there's real numbers and there are imaginary numbers. Is there something else lurking out there that I should know about that's about to hit me in the face? Well, I actually went over to our math department and asked, is there any kind of number or other number out there that I should be worried about? And the answer was no. Well, the actual answer was it depends on what you mean by a number, which is, of course, exactly the right answer. That's exactly what this person should have said. Now, he saved me from myself and said, okay, if you mean one that follows all the properties you normally associate with numbers, then no, there isn't anything else out there that you need to worry about. Now, there are other number-like entities out there. There's this thing called a quaternion, and it's used now for control systems. I guess quadcopters may use those as part of control systems. I've heard about something called an octernion that has 8 components. Not sure what that is, but it's out there. That's far beyond the boundaries of this class. So that's it. That's where complex numbers came from. That's why they seem so alien, because you don't need them for regular life. You only need them when you start using math to describe the technical world around you. You know, when you start applying, mathematical expressions of physical laws, they show up all over the place, and they're very, very handy. Modern technology almost wouldn't be possible without them, right? They're that critical. They're that fundamental. So with that, let's get back to the mechanics of it. So here's this. Your teacher told you that this would polynomials have roots where they cross the x-axis. I mean, that's what this says, but this one doesn't. But yet, it's got this. So they're saying, well, it doesn't cross the x-axis. Does it? Yes, it does. It absolutely does. It just doesn't do it here. Here's what this actually looks like, and we'll do this in MATLAB here in a minute. So if I take, instead of looking at this in 2 dimensions, I look at it in 3 dimensions, which you absolutely can do. Let me show you this. If instead of x, y, I have the real part of x over here and the imaginary part of x here, right? Now I'm looking at this essentially from the top. So y now comes out of the board. It's going towards you. This is a 3D plot, but I don't know how to do this 3D plot on my 2D board and make it very credible. Where the roots are, let's see if let's do this right here. Okay, now you can tell exactly where the roots are. One of them is right there. That's I. And one of them's right there. That's negative I. That's where the roots are. Well, why couldn't we see them before? Because we insisted on only looking along this axis. Well, they're not on that axis. No, those are there. And I'll show you here in a few minutes how we'll do this. We'll make a 3D plot, and I'll show you how to find roots of complex functions graphically. Now, a little more just sort of mechanics. A couple of things. What if I want to add complex numbers? How hard is that? It's not very hard. Let me get rid of this. Okay, so if I have a1 plus I b1 and I want to add a2 plus I b2. I'll do this in the abstract, and I'll make it real here in a second. Well, I told you that the imaginary parts and the real parts are independent of one another. So what you do is you add the imaginary parts, and then you add the real parts. So you get a1 plus a2, and you get I times, it's a bad b there, wait, hang on, b1 plus b2. That's it. There's nothing more to it than that. So if I wanted to add, say, 3 plus I plus 1 minus I, okay, just make up two numbers here, no problem. Add the real parts, so you get 4, plus the imaginary parts, well, that's plus I minus I, that's 0I. So you actually just get 4 on that one, right? So subtraction goes the same way. It's just the negative of addition, so no problem there either. How do you multiply them? Well, there's two ways to do it. I'm going to start out with what's called the Cartesian approach, and in another video I'll show you how to do polar. Okay, so let's do this. Let's say 1 plus I, and I want to multiply it by 2 minus I. And how do you do that? Well, about like you'd figure, the easiest way to do that I can think of is to just break this up, just to start expanding it out. So 1 times 2 minus I plus I times 2 minus I. All I did was expand this out. This is so easy a professor can do it. Well, let's see, that's going to like 2 minus I plus 2I minus I squared. What's I squared? Well, let's see. If I is a square root of minus 1, and I squared, that's got to be minus 1, isn't it? That's how that works. Okay, so that I'm going to replace with minus 1, so minus 1 is plus 1, and that looks to me like that's going to be 3 plus I, if I got that right. Yeah, I got that right. That's all there is to it. Okay, so super easy. Now, can you do this on your calculator? Depends on how much you paid for your calculator, frankly. If you have the TI-30, huge fan of the TI-30, I don't think it will do this. If you have one of the more advanced ones, like a TI-84 or something, I think it will, right? So that was multiplication. How are you going to divide these? Okay, now let's try division. I wrote this out again, same two numbers. Now we're dividing them instead of multiplying them. This is a little less obvious how to do this, but there's a technique that's very simple, and it relies on something called a complex conjugate. Do that over here. Now, complex conjugate is kind of a 50-cent name for something that's very simple. To take the complex conjugate of a complex number, you just reverse the sign of the imaginary part. So if z equals, I don't know, 3 plus I, what's the complex conjugate of z? Well, the conjugate of z is just 3 minus I. That's all it is. So why do I care? This is why you care. Let me take the more general case here, and let's say z equals a plus ib. Well, let's see. A plus ib times a minus ib, so multiplying a number by its complex conjugate. So if you work this all out, you get a plus minus abi minus I squared b squared. Well, that looks to me like that cancels out and you get a squared plus b squared. What that means is when you multiply a number by its complex conjugate, you get a real number, okay? That's handy. We're about to use that right here. So if I say that z is whatever that product is, I've got to somehow clear that in the denominator. If I could get that to go away, that would be great. Well, let's just do this. Let's multiply by 2 plus I over 2 plus I. Well, that's just 1, isn't it? I can multiply anything by 1 and I get the anything back. This is my multiplied by 1. I'm not changing anything. Well, so what this is going to turn out to be is 1 plus I times 2 plus I all over 2 minus I plus 2 plus I. So if I work this out, that's going to be 5, okay, 2 squared minus 1 is b is minus 1, but minus 1 squared is plus 1, so 4 plus 1 is 5, so I'm going to get 1 plus I, 2 plus I over 5. Okay, let me get rid of all this stuff over here. And if you work that out, you get 1 over 5 plus 3I over 5. All right, and that's it. Nothing more to it than that. All right, so with that in hand, let's go to MATLAB and try it on my computer.